Welcome to EE101-1, Fundamentals of Electrical Circuits.
In this video, our goal is to learn what is voltage divider principle and how it is being used in circuits. Next is to learn what is current divider principle and how to use it in circuits.
Hello, today we're going to discuss voltage and current divider principle. So when is it being used and how? Let's start with voltage divider principle. So if the connection is in series, then you can get the voltage drop across each resistor without getting the current. Okay, so in a series connection, we have only one current, right? Current is constant. Okay. So using this advantage, so we have here our general formula to follow in solving for the voltage drop using voltage divider principle. So it's the ratio of the resistor involved over the sum of the resistances, okay, multiplied by the total voltage. So for example, we're looking for the voltage across R1. Voltage across R1 is V sub 1. Okay. So V sub 1 is equal to the ratio of the resistor involved R1 over the total resistance multiplied by the total voltage. Same goes for the other voltage V sub 2. So V sub 2 is the voltage across R2. So we have here R sub 2 over total resistance multiplied by the total voltage. So as you can see here in our formula, we don't have any current, right? Like, since this is in series, current is constant. Current is the same for both resistors. So we make use of that advantage and we arrive at this formula. Okay? So again, remember the ratio, okay, which one is the numerator? So the numerator is the resistor involved. If you're measuring voltage across this resistor, so R1 is the numerator over the total resistance. So R1 plus R2, okay, plus the total voltage. And when you're looking for the voltage across R2, so you just have to get the ratio R sub 2 over the sum of the two resistors times total voltage. So let's have this example. For given V sub t equal to 15 volts, R1 5 ohms, R2 10 ohms. Okay, let us solve for the voltage across these two resistors, V1 and V2. So the total resistance here is R1 plus R2. So let's solve for V sub 1. So that is R sub 1 over R sub 1 plus R sub 2 times V sub t. So that is 5 over 5 plus 10 ohms times 15 volts. That is 5 volts. Next is V sub 2 equal to R sub 2 over R sub 1 plus R sub 2 times total voltage. So we have here 10 ohms over 5 plus 10 ohms times 15 volts. So that's 10 volts. So V sub 2 is 10 volts. V sub 1 is 5 volts. Let's check. Is V sub t equal to V sub 1 plus V sub 2? So we have 15 volts is it equal to 5 plus 10 volts? So that's 15 volts. So okay. So it's satisfied. So this one's correct. Okay. Let's try. Let's start this example. So here there are more than 2 resistors involved. So let's try solving this one. Okay, given is 20 volts total voltage. R sub 1 is 3 kilo ohms. R sub 2 is 1.5 kilo ohms. R sub 3 is 2 kilo ohms. So what are the voltage drop across each? What are the voltages across the resistors? Okay, V sub 1, V sub 2, and V sub 3. V sub 3. So the equivalent resistor. Okay, so let's solve for V sub 1 first. So for V sub 1, so here we added R sub 2 plus R sub 3, okay, because that is the equivalent of the two resistors here. Then the resistor involved is R sub 1. So we have here, okay, we have 3 kilo ohms over 3 kilo ohms plus 3.5 kilo ohms times 20 volts. So that is 9.23 volts. Okay, so let's solve for V sub 2. First, we need to get the equivalent resistance of the other resistor. Since they are 1, 2, 3 resistors, so let's get the equivalent of the other two resistors. So since we're looking for the voltage across R sub 2, so we need to add R sub 1 plus R sub 3. Okay, R sub 1 plus R sub 3 is equal to 5 kilo ohms. So applying to our formula, V sub 2 equal to the resistor involved R sub 2 over R sub 2 plus R equivalent to multiplied by V sub T or total voltage. So that's 1.5 kilo ohms over 1.5 kilo ohms plus 5 kilo ohms times 20 volts. That's 4.62 volts. Okay, let's proceed with the last one, V sub 3, or voltage across R3. So our equivalent 3 is, in this case, R1 plus R2. That's 4.5 kilo ohms. So, okay, let's solve for the voltage here. V sub 3 equal to resistor involved R sub 3 over R sub 3 plus equivalent resistance 3 times V sub 3. So that's 2 kilo ohms over 2 kilo ohms plus 4.5 kilo ohms multiplied by 20 volts. So that's 6.15 volts. Okay. So that is how you apply voltage divider principle. Okay. You use it to get the voltage drops across each resistor, okay, in series without getting the current. Okay, so that was mind blowing, getting the voltage without current. So that's so smart. So how about current divider principle? Let's go to current divider principle. Well, for current divider, if the connection is in parallel, okay, you can get the yes, you can get the currents, okay, currents across or flowing through each resistor without getting the voltage. Okay, remember for parallel connection, voltage is constant. Okay, there's only one voltage in this case. Okay, voltage across R1 is the same for the voltage across R2. Okay, so the general principle is, okay, the ratio of the resistor not involved over the sum of all the resistances multiplied by the total current is equal to the uh, current, which is you are solving, or the unknown current. So for example, this one, current I sub 1 is equal to R sub 2 over the total resistance multiplied by total current. Okay. Again, we're looking for the current that flows through in this branch. It flows through this branch. So the other resistor, the resistor which is not involved, is R sub 2. That's why that is our numerator. Okay. The same goes here. I sub 2, this is the current I sub 2 flowing through R2, right? Okay. So that's why the numerator is the other resistor or the resistor not involved, R sub 1, over the total resistance multiplied by the total current. So in this equation, there's no voltage involved, right? Okay. So let's see. Let's try some example. So we have this given, I sub t equal to 9 amperes, R1 3 ohms, R2 6 ohms. So what are the currents I sub 1, I sub 2? So I sub 1 is equal to the other resistor 6 ohms over 3 plus 6 ohms multiplied by 9 amperes. So that's 6 amperes. Solving for I sub 2, we have R sub 1, the other resistor, over R sub 1 plus R sub 2 times the total current. So that's 3 over 3 plus 6 ohms times 9 amperes. So leaving us with 3 amperes. To check, I sub t should be equal to I sub 1 plus I sub 2. So 6 plus 3, that's 9 amperes. So this is satisfied. What if there are more than 2 resistors? So let's try solving this circuit. So given we have 3.5 milliamperes, R sub 1 is 1 kilo ohms, okay, 1.75 kilo ohms for R sub 2, and 2.5 kilo ohms for R sub 3. So let's solve for the currents that flow through each branch. So first, let's get the equivalent resistance of R sub 2 and R sub 3. We're going to solve for the current I sub 1. Okay. So here we have 1.029 kilo ohms for the equivalent resistance 1. So that is R equivalent 1 over the sum of the two resistors. Okay. So now it's only 2 resistor, okay, because we got here the equivalent resistance of the two, right? So there are only 2 resistors involved here in this equation, Req1 and R sub 1. So that is 1.029 kilo ohms over 1 kilo ohms plus 1.029 kilo ohms multiplied by 3.5 milliamperes. Okay. So that is 1.78 milliamps. So that is our I sub 1. Let's go to I sub 2. So first get the equivalent resistance of the two resistors, right? So R sub 1 times R sub 3 over R sub 1 plus R sub 3. Because we're now here in I sub 2. Solving for I sub 2, the resistor involved is R sub 2. That's why we're getting the equivalent resistance of R sub 1 and R sub 3. Okay, because that's our numerator. So that is 714.29 ohms. So substituting, the numerator is 714.29 ohms over 1.75 kilo ohms plus 714.29 ohms multiplied by the total current 3.5 milliamperes. And that's 1.01 milliamps. That's for I sub 2. Last we have I sub 3, right? So get the equivalent resistance of the other resistors, R sub 1 and R sub 2, and that is 636.36 ohms. Okay, that's the equivalent resistance of that of those two resistors. So I sub 3 here is 636.36 ohms over 2.5 kilo ohms plus 636.36 ohms times the total current 3.5 milliamperes, leaving us with 0.71 milliamps. Okay? Summary. That's it. Thank you. Bye-bye.
Summary. The voltage divider principle is used to express the voltage across one several series resistors in terms of the voltage across the combination. The current divider principle is the process of finding the individual branch currents in a parallel circuit where each parallel element has the same voltage. That ends our discussion. Thank you for listening.